Welcome back to Sandman from Spider-Man 3 Explains. Today we're going to be doing some Boolean algebra problems that I think every computer science major should know how to do. And these problems come from the MIT 6.111 problem set that you can find publicly available online from their open courseware. And in preparation for my computer science final literally next week, next Tuesday, let's get to the problems. So Boolean algebra is essentially how computers work with binary numbers, specifically the CPU in a computer. So for example, let's say that we have two 1-bit numbers, x and y, and we're going to output x is greater than y. So this is something called a truth table. You input in values, essentially every combination of them. So for n digits or for n variables, you get 2 to the n rows. So this is 2, you get 2 to the 2 for rows. So in this case, x is not greater, 0 is not greater than 0, 0 is not greater than y, 1 is greater than 0, 1 is not greater than y. So we take a look at this row that provides the statement to be true. And so our Boolean expression is x, y naught, x and y naught. And this is a pretty simple expression, which we can easily make then into a circuit. So we have our x and our y inputs. We have x, y naught. So how do we go from here to there? Well, we have to use an AND gate right here. So this outputs to this box, which is usually an LED as an indication for your circuit workbench. So this x connects to this and the y is going to go through an inverter. And this is the circuit. This is inputting in x and y. X is greater than y. So x and y for x is greater than y. Now, this is a really simple example again, but these problems can get very, very, very complicated. Not all Boolean expressions are easy to simplify, as you can see here. This is an actual expression I had to simplify for a lab, and if I didn't simplify it down to like 2 or 3 terms, making the circuit for it would be impossible. So we have a bunch of rules and identities, as you see here, that help us simplify them. The most famous of which is going to be DeMorgan's Theorems, aka DMT.
Imagine going to a concert and half the people are doing mushrooms.
They pretty much just tell you how you distribute a knot for a parentheses. So A and B, you distribute the knot. This is A knot or B knot. And then likewise for A or B knot, this is going to be A, B. This is going to be A knot, B knot, which is just A, B knot, which takes us to the beginning. All right, problem number 6 on the problem set. Problem number 6. So in order to do this, we have to make use of the identity A or BC is going to be equal to A or B and A or C. So applying this rule to here, well, what is going to be A naught is going to be our B, B is going to be our C. So this is just going to be equal to A or A naught and A or B. So A or A naught is one of the identities we saw in the beginning. This just simplifies to 1, and that kind of makes sense. You're asking if it's true or false, which represents everything in Boolean algebra. So this has to be true. This has to be 1. So the final answer is A or B. And for this problem, we're applying the exact same identity, but backwards. So we start with the parentheses, and then, I see a common term, A naught and A naught. So I know there's going to be A naught or something. And what do we have? We have B and B naught. This becomes 0 because something can never be true and false at the same time. So this should just be equal to A naught. Okay, number 17. This problem had a deceptively easy answer. And let me just prove to you what it is. So we have this expression, let's just distribute the y. So yw or yx naught or yy, which this becomes a y, or yz naught. Now all of these have a y in common. That means that for the overall expression to be true, y needs to be true. So for this expression is equal to y. And using the same exact rule in number 20, so x or xy, we know that there's an x in both of these terms, that for x has to be true in order for this to be true. So this just becomes x. So this is equal to the x equals x. All right, this is DeMorgan's theorem, DMT number 2. Yeah, this kind of looks like a slightly big mess, but it's really not that bad once you use the involution rule. So that pretty much just means A naught is just A. Using this property, we then say that this whole expression, once you distribute the knots, I have to treat this whole thing, including the knot, as one unit. So this is equal to that. Never mind, my bad. The knot is still up here though. So this knot kind of distributes, and then we kind of use the DeMorgan second law to expand it right back. Like, wouldn't this just be equal to ABC knot or C not D? Yeah, that makes sense, because the knots kind of distribute in. So using this equation right here, we have two common C knots. And so we can kind of take them out. So this is going to be equal to C naught, A, B, or D. This is exactly what we were looking for. Now, as an exercise to you, the viewer, I want you to try out problems number 25 through 27 in the Boolean Algebra, as well as DeMorgan's Theorem 1 and 3. Basically, some of the problems I didn't do. Especially the Boolean Algebra problems, I feel like 25 to 27 kind of separate the A students from the B students. Now, after going through these problems aren't super hard. They just require you to think logically. But if you think about it, in real life, we make a lot of conditional decisions every single day. Should I go to the grocery store and see my friends, or should I study and not sleep? You know, there's the kind of decisions we do. And if we can simplify those decisions, making them becomes easier, and that adds less cognitive strain on our brain. But yeah, thank you for watching. I hope you found this useful.